Hi, this is Tim Kelly. Have you ever looked at anything and thought it looked simple, and then later on you saw the same thing and you thought that it was complex? Or the reverse was true. You saw that something was complex and then you saw that it was simple. And so you can have one object that has simplicity and complexity at the same time. And I don't quite know how to explain that, but I do have a word for it: beauty. This is we're having a video series called Chasing Beauty. This is the pursuit of fascination. You can go to a art museum and see a painting and wonder what is beauty. Look at the same painting every day for a month and try to figure it out. So what is beauty? Well, if we think that walking, if I asked you if walking was simple or complicated, you'd probably say that it was simple. You do it without thinking. But if you think about it a little bit more, it's so complicated, so complicated. And just watching people walk, watching families walk on the beach. I was at the ocean last week. It's beautiful. Circle's beautiful, ancient symbol of beauty and fascination. And I live in St. Louis, so I'm obligated to say the arch is beautiful, which I believe it is. If you're ever in St. Louis, please come see it. You'll be doing yourself a favor. Sometimes people face complexity and people tell them it's simple. And they struggle to understand. Yeah. And I was at the beach, took a walk on the beach in ankle deep water. And I walked for a few minutes. And I turned around to come back and I saw a fish. I saw like 10 fish. They were small fish, about the size of my thumb. There were 10 of them. Then I saw another 8, another 7. I saw hundreds of fish on the way back, but I didn't see them on the way out. So somehow I learned how to see fish in the water, and I didn't attempt to do that. It just happened. And so I was confused on the way out there. I didn't know what was happening around me. And so when I was walking the water, I was not anxious. And so we have this. So confusion is okay. That means you're ready to learn something. You're open to something. You're looking for something, searching, and maybe you'll find it. This is called the most beautiful equation in math. This is Euler's equation. And I read an email about 7 years ago. This man asked, I've been struggling trying to understand this for decades. And every year I come back to it and I try to figure this out. And I almost get there and then it's gone and I almost grasp it and I can't get it. So should I continue to try to understand the beauty of this? And I would say, yes. Go look at Grant Sanderson's video. It was amazing. It was so beautifully done. That was a great job, Grant. But Grant, even though he answered questions, he left questions open. And I had to see if I can figure it out. It looked like it was so simple, and it was a little bit more complicated than I thought. But I don't want you to necessarily have to face the struggles that I had. This is what I found. And maybe other people have already found it. But what we have is a unit circle on the left and a hyperbola, a unit hyperbola on the right. And so for every value that we use to compute a point on the left, we can use the same values to compute a point on the right. So we have a one-to-one correspondence between points on the circle and points on the parabola. So we can draw a line from the circle to the parabola. We can draw an infinite number of lines from each point on the parabola to the point from the point on the circle to a point on the hyperbola. So we have if we look at the bottom, we have the circular functions cosine and sine, and we have the hyperbolic functions cosine h and sine h. And then there's a midpoint function that later on in the video I'll call cosine O and sine O. What I call them early in the video, I also call them right and left. And so if we look in the at the top of the screen, we see cosine P and sine P. And that's defined as the segment from the midpoint of that line to the hyperbola. And the reason why I don't go the other way is then it would be negative, and this is a positive value. So there's two segments, one going from the circle to the midpoint and another segment midpoint to the hyperbola. And they're equal segments, same segment. So we see a very way to compute those values. You just use built-in function in Excel. There's a cosine h, and then we just compute the average of it. Pretty simple. This down the left side, we see that the angle is pi, and then we increase by pi divided by 15. And that's how we generated that screen, that chart above that we just saw. So the next set of columns, C, E, and G, compute the sine functions. So the cosine O and sine O are the midpoint on that segment from the circle to the hyperbola. And then we use those points to create these charts. We have the circle, the hyperbola, and then the third column is the midpoint. And then the fourth column is the connecting segment that connects from the midpoints to the circle and hyperbola. And so then we have the parametric equations on the bottom. And let's see, the first two are probably familiar with from you. And the second one is the average of the first two functions. And you can kind of see it. It looks mostly like the hyperbolic function. And that's because the hyperbolic function is up to a scale of 15 versus a half for cosine and sine. Should be, oh, it's up to over 1. Okay. And then the distance function, the segment function on the fourth column is similar to the third column. You're only like 1 different between the two if you measure it out. So let's go to the next. So here's all the values that were computed. We'll take a look at that. So we could actually run through and first do they're shifted, the title bar is shifted over to the left. But if you take the average of the cosine, which is 11.59 on the first row and -1, and if you take the average of that, you end up with 5.30. No. 5.77, -5.79. And then 6.30 and minus 5.77. Okay. So that would be, so if we take, say, the 5.3 and add it to the 6.3, we get the 11.59 back. And if we add the 5.77, -5.7, and add in the -5.7, we get the 11.55 back. And if we subtracted the two, then we get -1 and 0 for the cosine. So the last two columns are used both as an addition and a subtraction to produce the first 4 columns. So this chart double checks that the additions are correct and just demonstrates it. And so we have in the second column, we can see that the cosine P, so the cosine is the midpoint, cosine P is the connecting value, and then that yields the hyperbolic value. So we can see that we see the two equations right above it for the hyperbola, and we can see in the outline of that, we see at the top of the bar graph, if we look at the top values, that's the same as the blue line in the second column. Let's see if I can do oh, we can. Okay, so this line right here is the same as this line down here. And then if we take this orange S curve for the sun, we can see that is represented here, which is the sum of two. This is a stacked line curve and a stacked bar graph curve. So there's two, it's a combination graph. And then this one is going from the circle plus the connecting segment gets you to the midpoint. So here's the midpoint. And if we look at this blue line here, we can see that is being traced right here. And then if we look at this orange line, the sine line, we can see that outline right here. Now, one thing that we can't see are the components with the cosine graph very well. We can see the sine as the component, but we can't see the cosine very well. And so I stretched it out over here, and here we can see the cosine, a nice curved cosine there. So instead of thinking of all the equations and everything, it might just be simpler to go back to this and see, yeah, here's the blue figure, here's the orange figure, and there's lines that are connecting. That's all we're really saying. So that's why I want to put the equation in first, because it's easy to get lost. And it's actually pretty simple. You know, you can draw a line from here to here. That's why I like algebra or geometry better than algebra. So this story was that I went to take my son to a soccer game and stepped out of the car. My son stepped out of the car. And then a car pulled up in front of us. The man stepped out with his son. My son's wearing a yellow jersey. His son's wearing a blue jersey. And the other man said, "There's the enemy." And I said, "Don't you mean opponent?" And he said, "Yeah, opponents." And there were 7. They weren't enemies. So it made me think of the word opponent. I liked the word opponent after that. I thought of it often. And opponents aren't necessarily competitors. Opponents mean you face each other. So a mother and child aren't competitors. They're not enemies, but they do face each other. And so they are opponents. Opponents to face versus to oppose. Let's go back to the word that we started with. When I think of mother and child, sometimes it is a very simple relationship, very pure, very simple. And other times it is very, very complicated, most complicated job in the world. So on a beauty scale of 1 to 10, I'd give the mother and child relationship an 11 on the beauty. My wife has done a great job with our kids. Other opponents, floor, ceiling, walls. You got four walls and floor, ceiling, and they have 3 sets of opponents that all face each other. And opponents create a space between them. They create a space. Teachers and students should hold each other up as well, just like walls, And they create a space where learning happens. Finally, when you look at a mirror, you've never seen yourself in your life. Other people have, you never have. You see your opponent in the mirror. You do not see yourself. So an Irishman walks into a bar. The bartender says, why do you Irishmen always answer a question with another question? And the Irishman says, "Oh, do we now?" And so I'm Irish. The Irish are here to ask questions. They aren't here to answer questions. So I hope that at the end of this, while you may have a few questions answered, I hope you actually leave with more questions than when you started. Just my thought. Oh, here's a couple of good questions. How's the cosine an exponential function? When I looked at e to the ix, how in the world did that make sense? And I just always put that on my back burner. Hats off to on that explanation. So the exponents shoot off like a rocket, off to infinity, and they're in a hurry. And cosines just hang around forever, just enjoying the breeze and enjoying the waves. Grant had this picture of spiraling vectors. And again, a lot of this is based on his work, so please take his work. Before we get into this, and before we get to the next slide, I think, yeah, we go to the Taylor series first. So let me go over to Excel. I've got the Excel, I got the Taylor series machine ready. And I've got one in my X. If I come down here, I see that I have the Andrew Jackson number down here. So life is good. And if I bump that number, X goes to 2 when I bump it. And we see all these calculations that happen, all these calculations, 170 calculations to produce this number. And that is the EXP function when it gets the second power. So I validate that with the Excel function. So they both agree, so life is good. So I can bump this, bump, 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 and it goes across. And then I want to nudge it. Nudge, 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 nudge. And look here on this, on the edge. Whoops, I moved my graph. Look at this edge and this edge. And I'm gonna nudge it. And you watch that. And it's growing on the right and shrinking on the left. Bring it back. And it's growing on the right and shrinking on the left. And if I bump, 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 here, now watch this. I don't have to click it at all. I have this animated. Boom, 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 boom. Off it goes. Off it goes. Generating more and more and more numbers. Off they go. Cool. So this midpoint is at, when we're at 54.4, the midpoint is where, let's scroll over there, 54. Right there. That's actually, I think it's right here, 2.6078. No, it's 2.2857. That's the midpoint. And so what I do is I just take that midpoint value, I put it up here, and then I divide all of these columns by that. So we actually have a number with 22 zeros in there. Because this is the log of the midpoint. So there's 22.3 zeros in the midpoint. And so if I didn't divide, this number would go clear off the screen. You wouldn't be able to see it. And so when we do this waiver function, off it goes. We're up to 25 zeros, 26 zeros, 27 zeros, 29 zeros. Okay, bye-bye. Off the wave goes, growing on the right side, shrinking on the left. And then it moves to the right. It doesn't actually move to the right. It grows to the right. It grows to the right. And then it decays to the left. It doesn't actually move to the right. Okay, back to the PowerPoint. We're moving. We're moving. Okay, so I'm gonna skip the slide. Okay, this is an important one too. Okay, and again, I'm not going to go over this too much because Grant did such a good job on this, but we grouped the Taylor series into 4 groups: the right, the up, the left, and the down, which is, so when we have x to the 0, so if x is I, and we say I to the 0th power, we get a 1. I to the first power is 1. I to the second power is -1. I to the third power is minus I. Then we go back to x to the 4th. So then x to the 5th is I, x is it. So we keep on rotating like that. We keep on assigning these different expressions to different functions. So we split up the Taylor series into four functions: the right function, up, left, and down. So what's kind of odd about that is that the cosine goes both right and left, right? It can go to +1 and to -1. So the cosine is made up of the right and left function. The sine function is made up of the up function and the down function. So the question is when you go right, where do you go to? And when you go up, where do you go to? Because you go right over there, but where's there? So what I did here is when I divided the columns, the Taylor series, into different values for right, up, left, come back here, left, and down. Each one of these columns is assigned to one of those directions. And so the question when I watched Grant's video is, well, are there 4 functions for right, up, left, and down? Does this make sense? And here's the group number for the power. So I to the 0th, or x to the 0th, or I to the 0th, x to the 1, x to the 2, x to the 3, back to x to the 4. So the question is, what are the points along the way? You're going somewhere. You're going somewhere. You're doing a whole lot of calculation there. Heck on this Excel spreadsheet. You're doing a whole lot of calculation where are you going to? And to be honest, I already told you the answer. You're going to the midpoint of the circle and the parabola. But we're not there yet, so you don't know that. Okay, so these are the Taylor. Just Google the Taylor series exponential function, cosine function, and sine function. You have this well known for however many hundreds of years. And because of Grant's explanation, where he told us how the vectors going to the right all had a factor of 0, 4, 8, 12, 16. We know that all of those terms go to the right. And so and we know that x to the 1, 5, 9, those are all the terms that are going up. X to the 2, 6, 10, so on. Those are the ones that are going left. And x to the third, 7, 11, those are the ones that are going down. But we don't know where they're going down to. We know that's correct because the formulas up above are correct. They're taken straight from the formulas above. So with these definitions, with the definitions that are on this page, we can see that cosine of x is equal to the right of x minus the left of x. So I'm down here at the bottom of the page. And sine of x is equal to up minus down. And right, e to the x is going right plus up plus left plus down, which is interesting when you say that, because people are always telling you, oh, you have to go this way. You have to advance yourself. You have to move. You have to move. Move in which way? Well, if you move in all directions, you actually stay in the same place and you just grow. And that's what this formula is saying. This is the formula for growth. You add the right, the up, left, and down. You add them all. And so you may not be moving at all, but you're growing. And it's funny that equation actually just does it. What are the points along the way? Okay. Yeah. Why the long detour? Yeah, that's true. There's this huge detour. And we have these equations. So the equations on the previous page are correct. But that doesn't mean we know where this top right corner is. Where's this top right corner? Well, I spent a little time and found it's on the midpoint of the parabola. That's where it actually is. I was going to leave you in suspense, but I don't think I will leave you in suspense. It's the midpoint of the parabola. That's it. Whoops. So yeah, this is exactly what I'm saying. You can either go right, up. Now you can go left or right. And then you can go up or down. So the same values, the same functions can be used to get to a circle or to a parabola. To be honest, it kind of blew my mind. Ooh, now, okay, we've gotten to the point where we get to go back to Excel. Yes, I love this. This is probably my favorite part. First, here's the power group. You already saw that. This one here, I rearranged the Taylor series into 4 rows, and I gave the names of right, up, left, and down. And so when we do the bump, look, it's changing all those numbers. That is so cool. So cool. And there, that's all you have to do. I've got all the I terms up here. You just say the power of x to the d sub 1, and then divided by the factorial of d sub 1. Is that beautiful? That is just so cool. So I just duplicated that function here. And one thing that I did is here, I called this variable x, but I'm going to have an output and it's going to be called x. So I renamed this variable to be called t. So there was no confusion on here. It's the variable t now. And so I created these variables called right 148, up 148, because there's 148 terms. That's where the 148 came from, where everything is less than 148. And I go ahead and compute the exponential, which is the right, up, left, and down. And then that's pretty much all you need to see. I'll show you this. So we'll go back to here, back to 0. And then we'll come over here and we'll press my button. There we go. Oh my God. Now it's slowing down because on my machine, it's very smooth when it just runs, but because I'm recording a video, it slowed it down a little bit. It's not quite as smooth as when I normally do it, but it's smooth, so I see it. So if you download this Excel spreadsheet, you should probably get it where it's very smooth. But you see this wave move across. And those 4 colors are for right, up, left, and down. So it breaks so if you took the sum of all the rights, you come up with the number. The sum of all the ups, that would come up with the number. All the lefts, that would come up with the number, and all the downs, that would come with the number. So you just sum all of those together, and you get your 4 numbers. And the thing that's amazing about this is that if you compare right to left, they have to be within 1 of each other. All those computations, and there's a difference of 1. And they do the same thing for up and down, and they have to be within 1 of each other. And the same thing for all of these. They all have to be. This has to be almost a perfect square. It's not a perfect square. It's off. And because it is off, it draws a circle. But like, look at this. Going up to the midpoint of 50 zeros. rows. 50 zeros. And that's just for one column. It's crazy. Look, the right. What's going on there? So, all right, going back to this, to the power series. Okay, that was a power series. That was kind of fun. Okay, we're gonna go over average and average difference. Average you already knew. And an average difference after you know about it, oh yeah, that's obvious. And I just called it the average difference. I just made up that name. Because I didn't see it defined anywhere. It probably is defined there, but let's just go through this real quick. What's the average of 1 and 9? 1 plus 9 is 10, divided by 2 is 5. What's the difference of 5 and 1? 4. What's the difference of 9 and 5? 4. So the answer to both questions is going to be 4. That's always going to be the same. It's always going to be the same. You could also do it by saying 9 minus 1 is 8, divided by 2, that's 4 also. So you can get to it through 3 different equations. And then once you get the 4, so you can produce the 4 from 3 separate equations. 9 minus 1, 5 minus 1, and 9 minus 5. They'll all produce the same answer of 4. So I could actually change that 4's answer to 3 questions. So now, what's interesting about that is that it's kind of an odd, it's kind of a strange quantity, because that quantity 4 is, when you combine it with 5, it produces 2, 4, and 10. 1 and 10, 1 and 9. Why? Like, I had to change that slide. 5 plus or minus 4 is 1 and 9. I don't know where I came up with that, 4 and 10. Okay. So if you say 5 plus or minus 4, minus the 4, it gives you the 1, plus the 4, it gives you the 9. But that 4 quantity, in effect, is a plus or minus quantity. So you could say, combine this 5 with the 4, whatever it is. So that's from a programmer in me. It's a different class of number. It's not your ordinary class of number. Most numbers, when you combine it with other numbers, it doesn't give you both 1 and 9. Like your average everyday run-of-the-mill 4 doesn't produce a 1 and 9. You combine it with 5, but this type of 4 does. So if you have a value and then you change it, so one thing you want to do is make a small change in your function and see what happens. That's why I'm having the bump and the nudge on the Excel spreadsheets. Lets me see what a small change affects on the output side. So we're doing that. We take the top row is pretty easy. 1, 9, 5, and 4. This time I got it right. And negative 1, 9, 4, and 5. So I changed the only thing that I changed on the input side was the negative 1. And the outputs changed in opposite directions. So the third and fourth columns are acting in opposite ways. And so I call them opponent functions. And there's another reason why I call them opponent functions, and that's because they define a space that is very close to each other. We'll see that later. So opponent functions are defining a space as well. Okay, so here's an opponent function. This is, I actually used this back in high school when I was taking a typing class where we typed on paper. And you had to adjust the leftmost margin, because when you indent on a letter and you got to a quote, you had to indent. You had to indent the column so that your quote was indented. So there was different levels of indentation. And so when you needed more space, you would decrease your left margin. So you move it to the left. That would decrease your average, the middle of your page, but it would increase the amount of room that you had on that page. And so that's why you had these crossing lines. You know, the averages, so the average difference, you could also add the room on the page, the amount of space that you have available between the low and the high. So that's what all these graphs are showing. The whole page one is kind of nice because it has a nice straight line across the top, because the size of your page isn't changing. You're changing the leftmost margin, and that's changing the average plus the amount of room that you have on the page, but the page size didn't change. So I called it average difference. That was just my own name for it. So don't go, I tried to find something that should be a fairly common term, or, you know, there should be a commonly defined term for that, but I didn't find one. So this is the if we look across the top column, I'm sorry, the titles are shifted wrong, but you have a low of 5, high of 80, the sum is 85, the difference is 75. No magic here. Average is just 85 divided by 2. The average difference is just the 75 divided by 2. Okay? No big shakes. Average minus the average difference. 42 minus 5, 42.5 minus 37.5 gives you back your 5. So now we've got this function is taking these variables and reproducing back the 5. So we're going back in the other way. Now the average plus the average difference gives you back your 80. So the 42.5 plus 37.5 is equal to 80. Okay, so and as you change that, you see that if you compare these two columns, this column 37.5 going is increasing 37.5 to 8, but this value is decreasing. Okay. All right. So in this case, the high value is constant all the way down that column. So what happens when that column changes? And that's what the next graph shows. And again, this is no big shakes. It's just the high number is increasing from 2 to 8.23. So it gives you this nice, pretty curve, goes sloping upwards. But look at these other 3 curves, the black line, the red line, and the blue line. What's happening here? Well, the black and the blue line are increasing together, right? When this black line goes up, the blue line goes up. But when the blue line goes up, the red line comes down. And then we get a vice versa. Black line's coming down, blue line's coming down. Red line is contrary to that. It goes up. Okay? Simple stuff. Simple stuff. But we use these functions. We defined average and average difference as functions. Now we're going to use those. Okay. Here they are. Just because it's cosine and sine and infinite series, don't let that fool you. This is still simple stuff. It is really simple. It looks worse than it is. Okay. So the right, we already know that that's 1 plus x to the 4 over 4 factorial, x to the 8th over 8 factorial. And if we look at these equations, you might be able to do it in your head. We're going to do it the long way on the next page. Here, we'll go there, and then we'll come back. Might make it simpler. Okay. Here we'll do this once, and then we just repeat the same steps 4 times. So this is saying, how do you get from cosine of x and cosine h of x and get to the right of x? Well, it's just 2 steps. Adding the first 2 equations, we get 1 plus 1, that converts over to a 2. X squared minus x squared, those cancel out right here. X to the 4 plus x to the 4, that's 2 times that. Then all we have to do is divide by 2, and we get cosine of x plus cosine hyperbolic of x plus the cosine, the circular cosine divided by 2 is equal to 1 plus x over 4 to the 4th plus x over 8 to the 8th, on down the line. So I'm going to let you look at that for just a second. You can pause the video if you want. But I didn't show it, but I'm going to leave that as an exercise for the user. What if instead of adding these 2 together, you subtracted these 2 together? So now this plus 1 would have been a minus 1, and this minus x2 would have been a plus 2, and this x to the 4th minus 4 is a minus x to the 4th. So now what that means is that for the subtraction of these 2, you get the x to the 2 terms next to the 6. I'm going to go back to that. So if we look at the right and left functions, we're looking at x to the 4th, 1, x to the 4th, x to the 8th, and we just did the work on to show that this does actually produce, or that this value here, this formula here, actually generates the same thing as the right function. These 2 are equal. And then this formula, how do we interpret that? If we want to just remember what it means, all that is just the average of the cosine h and the cosine. That's just the average function. Okay. That's why we defined the average function first. So we had this form. So this one, if instead of adding these 2, we subtracted them, I'm not going to go through that. I think some people will be confused by it, but I just don't have time for that right now. I'm sorry. but you end up with x to the 2, x to the 6th, and x to the 10th if you subtract them. And so this formula where you say this value minus this value over 2, that's the average difference. So when you combine these two, you have the average and the average difference of cosine h of x and cosine of x. So the average, you know what it, everyone knows what an average is, but the average difference is basically how much room is there between those two. So what is the distance between these two divided? What is the share between these two? It's not the total difference because half of the distance goes to the cat cosine h and half of the distance goes to the cosine 2. But what is the shared difference? So half goes to you, half goes to me. And then on the sine, we're doing the same thing. We get the average of the sine is the average of the sine is the average difference of the sine. And then that term, average difference, may not be the best. It may be confusing. If it is confusing, I do apologize. Okay, we've shown the work. And then this was, this is why when I was thinking about these functions, this graph, when it was in my head, that's why I started calling them the opponents. Because this red and light red or pink, they're paired up and they will always be within plus or minus 1. You can barely tell them apart. I mean, they're going neck and neck all the way down. The blue ones, the dark blue and the light blue ones, they're the same way. They're always going to be together. And so they come from different, they come from different places, but actually in the end, they're all wrapped up to each other. So if you, let me go over to the Excel spreadsheet. I can show you that a little bit better. If we look at the opponents, that's this right here. Okay. And if we zoom in, okay. So we have these functions zoomed in and they get really close. All of them go extremely close and they're growing exponentially. So they're going up like a rocket. And if you zoomed in on them and actually had to zoom in on this and split them apart. And so they're actually much closer than even this diagram shows. I had to stretch them out in order to get them to print where you could see them separately at all. So you have the cosine O, which is the midpoint, and the cosine or the average. This is the average difference or the connecting segment. So I have different words to describe the same thing. That's a midpoint and connecting segment. And then this is the midpoint and the connecting segment. So these guys will just keep on circling each other over and over and over again, every pi. So, and now we're at the final goal here. We did it. I honestly hope I did not confuse you, and I probably did. Show the current slide. So what did we see? We saw these 4 new opponent functions. So we had 2 new, I started off calling them the left up, or the right up, left down functions. And then I ended up changing those over to be calling cosine functions. So the cosine functions are named O and P because of the word opponent. So the O is the first function going to the right, and the P is the second function going back to the left. On the sine function, the O function is the first function going up, and the left function, the down function coming down. So if you look at this guy right here, this is what I'm talking about. That's why I kept on showing that. So we have these 4 new opponent functions. And then to kind of give you a good feeling about opponent functions, because it's kind of a term that I just made up. I just talked to you about averages. Everyone is comfortable with averages and stuff. So average and the average difference. The average difference is the term that I made up also. So opponent and average difference, I made those up. I hope I didn't confuse you. And if you have a better name for it, I'm open to it. That's not written in stone. Okay, so what did we see? We saw, okay, we had the 4 opponent functions, and there are also component functions because you can compose sine, cosine, sine, and cosine h and exp from those 4 functions. You can just do them with addition and subtraction. It's crazy. Oh, we saw the color Taylor machine in Excel. I actually spent quite a bit of time on that, and that was fun. And that's available for anyone who wants to have a copy of it. And then hopefully you saw the connection between the circle and the hyperbola. And so we saw, I hope we saw a little bit more of the beauty of the Euler's formula, and that this might have given you a few answers, and hopefully it sparked a whole bunch of questions in your head. So, and I'll leave you with a few words to remember. This was from the vocabulary of what we spoke with today: simplicity, complexity, confusion, opponents, and most of all, beauty. Have a good one, everyone.